Greetings, everyone, in our Calculus for Teachers class. This is a short video introduction to get you started on Project One. Where do I find Project One? Well, I put it in communication and documentation. Since it spans several weeks, I didn't think it belonged in any one week of the course. So let's go ahead and go into communication and documentation. And we go in there, you can see that there towards the bottom is Project One. And let's go ahead and read the description. So opening this up now in my PDF viewer. I guess I got a couple copies of this. There it is. So let's just read through it. Calculus is often described as the mathematics of change. Differential calculus, where the derivative is developed and applied in a wide class of functions, seeks to quantify the instantaneous rate of change of one variable with respect to another. So this is what we're learning about in the course, is differentiation. So it seeks to determine how fast one variable is changing for a given value of another variable. This tool is really highly applicable in a world full of quantities that depend on one another. So in this project, you will apply the notion of the derivative to either one or two different real-world settings to produce tabular and graphical representations of how data is changing. Be aware that the second project in the course will ask you to find algebraic representations, that is functions, for each setting, which will allow you to find derivatives algebraically. So anticipate that this is sort of a linked two projects. There'll be a follow-up later that'll employ an algebraic approach to the same data. Now, I did change this project this week to make room, I guess, for the great variety of learners that we have in our course this year. So if you consider your knowledge of calculus strong, then I'd expect you to carry out analyses of two different real-world settings. If you consider your knowledge of calculus still developing, then I would expect you to just do one. And finally, if you're really up for a strong challenge, I'd encourage you to find your own data set and carry out a similar analysis on each of the sets that you find. So what are the requirements? So for each data set you analyze, complete the following. Use technology to create a tabular, that is a data table representation of the function and its first and second derivatives, and explain briefly how you constructed the table and provide the first 10 rows of the table if you're in your write-up so the reader can understand. Some of the data is fairly large, you'll want to just include 10 rows so that we can understand. And then go ahead and make three different graphical displays of the function. So a display of the function, a display of its first derivative, and a display of its second derivative. And be sure to scale your axes in each display to ensure the reader can fully view the way that the function is changing in each setting. And then finally write a short summary that summarizes what you've learned about this functional relationship by examining the function, its first and second derivatives, and be sure to include units in your analysis and make at least 3 observations for each of the 3 settings. So you can include annotated graphs when appropriate. So in other words, a picture of the graph with your thoughts written on top of it, maybe pointing to special spots or points to give you a sense, give us a sense of your understanding of calculus and its application. So what are the data sets? There's a description of the data set below. There's 4 options to choose from. Once again, the most you would do is 2, and some of you only do 1. So the world population data set is just what it sounds like. It's world population every year from 1950 to 2015. Some questions you could ask is, how is it changing, the world population? How's the rate of population changing in the recent past, and how's the rate of change of population? Is it accelerating or decelerating? Over which periods is it doing that? There's one data set if you're a geometry fan. This might be for you. The data set was obtained by calculating the volume of an open top rectangular prism. That's just a fancy way for saying an open top box that can be created by cutting squares out of each corner of a piece of 8.5 by 11 inch paper and folding the sides up. So it provides the volume as a function of s, the side length of the square that can be cut out of each corner. So think of it as, you're just taking a little square of paper out of each corner, and then you're left with 4 flaps, right, that you can fold and fold up. So if we took just a little centimeter square out of each corner, we'd have this very shallow box that would have, a great surface area on its base, but not much height, right? Whereas if we took a 5 centimeter square out of each corner, we'd see something with a much smaller base area, but quite 5 times the height. I hope you can picture that in your head. If not, just try it. Cut a square out of it's the same size square out of each corner of an 8.5 by 11-inch paper and fold it up and think about the volume and how you'd calculate that. So, what are the limits to the scenario? What is the biggest and smallest cut that can be made? How does the volume of the box change as the size of the square cut out of the paper gets larger? And how does the rate of change in volume with respect to the cut change as the cut gets bigger? And what does the second derivative tell us about the way the rate of change in volume with respect to the cut is changing? And is there some cut that maximizes the volume? And how do derivatives help us find this cut? One more is NBA draft pick salary. If you're a sports fan, this might be for you. The data set provides the starting salary offered to the top 30 NBA draft picks last year. Actually, I think this has been a couple years ago, so that's a little outdated. I'm sorry, I used this a few years back. It provides the salary as a function of draft picks, so important questions might be asked of this data include the following. How are salary and draft pick related? That is, how does salary change as a function of draft pick? I mean, obviously, you would think that the first picks would have the highest salaries and that things would go down from there, but is it sort of uniformly down, or how does that work exactly? And then how does the rate of change of salary with respect to draft pick change as a function of draft pick? So how is the first derivative changing? And what does the second derivative tell us about how that rate of change with respect to draft pick is changing itself? And then the last one, if you're sort of a nature lover, maybe this is for you. The data set provides the length of day from sunrise to sunset in Missoula, Montana for the calendar year. So that it provides the length of day as a function of day number for the calendar year 2015. So I've also included both the length of day in hours, minutes, seconds, as well as like a decimal equivalent, which might be easier to work with. Some interesting questions is how are the day length and day related? What day is the longest? What day is the shortest? How does day length change between these two extremes? And what does the graph of change in length with respect to day teach us about how length changes throughout the year? When is the change happening the quickest? When is the change in length the slowest? And what does the graph of the second derivative tell us about when day length is accelerating, decelerating, or staying the same? I don't know if you've noticed this, but there's some days, periods of the year when it just seems like the days are getting longer so quickly. And there's other days when it just seems like, and this is for me always in the winter, when it just seems like there's so much darkness and there's just very little light, and it seems like the length of day is just not changing at all. So that might be an interesting question for you to analyze if that's a curiosity for you. Now, I don't really want to do any one of these because I want to leave room for you to make your own discoveries, but I do want to do just a quick example to give you a sense of what I would expect you to do with a set of data. Most of you probably read in my introductory statement that I'm a big bike fanatic. I love bicycles and own way too many of them, and so I thought it'd be fun to pull something I'm passionate about into analysis here. And again, if you're up for the extra challenge, I would encourage you to do the same. Find something you're passionate about. If you can find data on it, carry out this analysis on that data. So I'm going to pull down just a brief sketch. This is going to be very abbreviated. It won't be a finished product, but it'll give you a sense of the kind of analysis I would expect you to do. So, what I did is I went out to the internet and I just sort of took a look to see if I could, how many bikes are made in the world, every year. And I found this kind of neat graph. This is world bicycle production from 2050 to 2018. What I thought was interesting is that we had this sort of increase and then a decrease, into the 2000s. And then it seems like it's increasing again, maybe. But or maybe this was an artificial, bottom. I'm not sure. It'd be interesting to know the small, I guess, stories. I also found it very interesting that right after, the 1970, the early 70s, there was this sort of uncharacteristic increase. And also it's sort of in 87, 88, there were these two big spike years, as well as in 2004. I thought it was kind of complicated data to I guess, analyze on its own. It's not a smooth trend. So to kind of smooth the trend out, what I did is I just took it on a 10-year increment. I started in 1950 and I ran it all the way through 2010. And these are the millions, the number of bikes made in the millions in the in the world. And so this is sort of where I would expect you to start with this data. And of course, the first thing you're going to want to do is get a picture of what this looks like. So I don't know if you're aware of this, but if you just highlight, and I'm in Excel sheet, sorry, not Excel, but Google Sheets. You just highlight this, and then I control copy or edit copy. I use the control C. So I went ahead and copied. You can go then into Desmos, which I've shown you once before in a video, but if you didn't watch that, we're at desmos.com. Get yourself signed in and get a free account. But if you just type into an open cell and hit paste, and for pasting into Desmos, there is no paste button here, I don't think, but you can do Control V, as in Vespa. So pasting will give you this. So that's what I did above here. And then of course you can relabel if you want. So I'll just get rid of that since I already have it above. And then what I did is I added a little note, to here and said below is the data for world bicycle production from 1950 to 2010. Figures are in millions of bicycles. So there you can see a graph of I guess this function, bicycle production as a function of year. If you want to get a picture of this, of course, you can export this. I think here, maybe not. How do I export it? Oh yeah, right. It's right here. It's this share graph. So you can either, get a link for it. If you want to put a link into your report, you can. That's fine with me. Or if you're an image person, you can export an image and you'll get this type of an image. And you can obviously sort of change things here if you'd like. You can do small squares, or you can do an extra large square. Anyway, you get the idea, and it will download as a JPEG or a PNG. You can also get an SVG, but usually a PNG works just fine. Portable network graphics. Okay, so that's really the first part of the first graph that you need is a picture of sort of the function itself. And then the next thing you need is you need to get a sense of its first derivative. And I don't know if you can kind of look at this graph and think to yourself like, okay, we're really talking about the slope of this line from 50 to 60, the slope of this line from 60 to 70, slope of this line from 70 to 80, the slope of this line from 80 to 90, 90 to 2000, 2000, 2010. We can obviously see that things are getting steeper until I get to about right here, and then we hit some sort of an inflection point where the steepness now starts to fall off and we get shallower as we come forward in history. Kind of looks to me almost like, we're approaching some limit, like the number of bicycles the world is capable of needing in any one year. But I find it interesting to think about. But let's go ahead and talk about how you could just let Excel, or in this case, Google Sheets, calculate this. What I'm really asking here is like, how much did this change per year across the 10-year interval? And of course, we know that to find the slope, we just do rise over run. So way that you can work in any spreadsheet software to make calculations is to start with an equal sign. That means I'm going to make a calculation, and then you can use the cell values. So what I want is I want this cell, I'm clicking on it, minus this cell, I'm clicking on it, ending parentheses, that's the rise, divided by, now you need parentheses for run, of course, because the division has to be by the whole thing down there, 1960 minus 1950. And what I find out is that the first derivative, I guess in 1960, if I'm sort of thinking of it as from 50 to 60, is about 0.9 or 9/10 of a million bicycles per year. It's increasing, which kind of makes sense, right? Because we increase by 9 million across a 10-year interval. So 9 million divided by 10 is almost a million bikes per year. So 9/10 of a million bikes per year is the rate at which the graph is increasing across that first interval. So in other words, if I go back here, this rate of change is 0.9. So I would expect this rate of change to be quite a bit more, and this one even more. These two might be comparable. So let's go ahead and see what happens. Here's the nice thing about any spreadsheet software. This little square in the corner is there to draw your attention, because what it says is, do you want me to copy and drag down? So again, if I just grab that corner and drag down, I know it's kind of hard to see, but there's a little dotted lines. What it does is it basically repeats that procedure now for these next 6 cells or 5 cells. So basically I got my first derivative there by just doing one and copying it. So I will say you can either write rate of change or first derivative or something like that. One thing that's always interesting is that you don't get a first derivative value for the first data point because, of course, there's no way to sort of tell what it was doing in 1940. So you always get one less, I guess, data value for first derivatives than you do in the raw data. So that's kind of interesting. We can see that the rate of change is the highest in the period, I guess, leading up to 1980. Oh, sorry, I'm wrong. Period leading up to 1990. You can see this value 3 is the highest. So that should be reflected in the graph, right? Leading up to 1990, it's this one where we saw the largest jump in value, and I guess the estimate is about, the number of bikes being sold is about 3 million per year, is the rate at which it's growing, that the first derivative is growing. I hope that makes sense. Sort of the next thing to do would be to get a sense of what that graph looks like. So what I would do is I would copy this data. How would I do this exactly? I mean, what I really want is I want to plot this year, these years, right? Oops. Oh, let's just undo that. I want to plot these years against these values to get a sense of the graph of the first derivative. And so that's what I'm going to do. I'm just going to copy these. So I'm using Control C to copy. I'll put it over here. Well, I think I want it right there. And then I'll do this as Control C to copy. Except for I want that paste to be paste special and to do the values only. And the reason I want values only is that I don't want it to copy the formula that's calculating that. So values only didn't work. Let's try that again. I don't know why it didn't work that first time, but I stopped and I'm just highlighting that and I'm hitting copy, and then I'll highlight this and hit paste special values only. There it goes. So this is year and first derivative. And now if I just take that and dump it into my I guess I just paste, so Control V gives you this. And one thing I just want to warn you about is don't give me this graph. I can see that it's definitely the highest in sort of 1990, but it's really hard to tell what's going on there. I don't know about you. So what I would do is I would turn those off, and I would extend, I would change the axes on my graph to get a better picture of the first derivative. So I'll go into graph settings, and what's going on is my y-axis is way too big, -68 to +149, when the values I have are all in the sort of 1 to 3 range, right? So what I really want is I want something that starts at sort of like, I don't know, -1 in the y and runs to 3. So there we go. And when I do that, I get something that looks like this for my first derivative. Boy, it just goes way up and then crashes and comes back down, right? So that's a picture of my first derivative, the rate of change per year of bikes being sold in the world in 1960, 70, 80, 90, 2000, and 2010. So we can see that we have some sort of function that's definitely peaking and then dropping off. And I hope that makes sense to you, because we definitely see, the rate of change changing extremely fast, right? Between 80 and 90 goes up by 30 million bikes per year in 1980 compared to 1990 across a 10-year span. So increasing about 3 million per year, which is what we're seeing on the left here is 3 million. Hope that makes sense for the first derivative. And of course, for the second derivative, we just do the same thing, right? Except for on the first derivative's data. So I'm going to move this over. There it is. And I'm going to put the second derivative here. And all I want to know is the rate of change at which the rate of change is increasing or decreasing. I want to know how much it went up, 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 and then I'm going to see it definitely went down here. So I'm going to have a mix of positive and negative second derivative values. So again, it's the same equal. I want this to be this number minus that number divided by parentheses year minus year. And again, I'm going to get 1. We'll go ahead and hit the autofill. So I can see that right here it went up about 7 tenths, 7 100ths per year. So the rate at which things were increasing is going up. So it's accelerating. But it peaks out in the period from 1970 to 80 at about 1/10, and then sort of starts to back off from 80 to 90, and then turns negative in 90 to 2000, and in 2000 to 2010. So again, I want to plot this as a graph and try to understand it. So I will take just these years, 1970 to, oops. I'll copy those ones and put them over here. And I'll copy these ones and put them over here. And remember, paste special values only. And I want year and second derivative. We'll just edit this. Year and second derivative. And we'll get a picture of this guy as a graph. So I guess I'm going to World Bike Production. And let's go ahead and turn off this data and turn on some new data. Second derivative, again, there's the second derivative. And I want my y-axis. These are, again, very small. So, I don't know, negative 0.1 to, I guess our highest value is about 0.1. So I'll go to 0.2. There we go. And I'll click off of it here. So again, we see sort of, we see that the second derivative tells us that sort of we have, positive values, the rate of change, although it's starting to slow and decelerate as we get to here, but somewhere between, it's weird, you can't really see the value for 2000. I think it's buried. Oh no, it's off the charts. That's right. There's 2000. It's boom, and then back up. So in other words, there was this real big change in the rate of change of the rate of change of bicycle production in between, I guess, 1990 and 2010. 2000. That tells us a little bit about where the graph, you remember that the second derivative tells us that the graph is concave up when the second derivative is positive and concave down when it's negative. So someplace between, I guess, 1990 and 2000, we see the concavity switching from concave up to concave down. So let's see, what can we conclude from all of this? I guess one thing to note is we would look at the graph and talk about, how's it changing? Well, it's obviously growing, right? But it's growing and seems to be sort of decelerating. When I look at the first derivative, I can see the rate of change, and we can see that things are accelerating up until 1990, and then they're sort of decelerating past 1990. And that's exactly what the second derivative shows us, is that things are concave up, indicating acceleration up until 1990, and then concave down past 1990, indicating that we're definitely slowing down in the rate of change in which bicycles are being produced in the world, starting in about 1990 or shortly thereafter. I hope that gives you a good sense of sort of roughly what I'm looking for. I would expect pictures of these data points and then some sort of write-up, about what you can observe from the 3 graphs that we constructed. I think I asked you to make 3 observations per graph, so there'd be a total of 9 observations. And of course, you can write on the graphs, annotate them. I'm not looking for a polished academic report. I'm looking for a demonstration of your understanding of rate of change and use of some of the terms that we've used in the course so far, like derivative and first and second derivative, concavity, and acceleration or deceleration in terms of rate of change. I hope this makes sense, and I hope it gives you a good sort of head start into sort of framing what it is you'll carry out in your project. And I hope that you can find a data set that you're interested in. If you have any questions, please don't hesitate to reach out to me, and I really look forward to seeing what you come up with, and we'll talk soon. Okay, thanks. Good luck.